Hello and welcome to Chapter 11. This is a chapter on forces, and Section 1 we're going to start with how forces change motion. We're going to start with defining force as just a straight out push or a pull. There are three types of forces. There's a contact force, so you actually touch the object that you're pushing or pulling. And then there's gravity. That's a pull that's towards, well, for us it's towards the earth. If you're out in space, gravity is towards the large object floating near you. And then we have friction as a force. This is the force that resists motion, and it's between two surfaces. So if you're trying to drag something across a surface, friction is the force in between them that resists the movement. So you got a push or a pull, you've got gravity, and you've got friction. Net force is the term we use to describe the overall force acting on an object when all the forces are combined. So if you've got a push or a pull and you're pushing, let's say you're pushing a box along the ground and you're pushing it with this much force, but friction is saying, no, I think you ought to slow down a little bit. If you take the force you're using minus the resistance force, that's going to be the actual force that is moving the box, and that's called the net force. So it's kind of like the answer to an addition or subtraction problem, okay? If the net forces are zero, then the forces are balanced, and it's like having no force at all. So if I'm pushing a box, and I'm pushing and I'm pushing and I'm pushing, I'm pushing with all this force, but the box is really heavy, and I can't move it. The force of gravity is actually keeping that force, that box, still. So I'm pushing, but gravity is holding a lot harder than I'm pushing. So there's no movement that's happening. That's a net force of zero. An unbalanced force will change the motion of an object. If I'm pushing a box across the floor and the box is not that heavy, then the gravitational force pulling it down is something, but the force with which I'm pushing is a lot higher. So it's my force minus the gravity equals the net force, and there's an actual number there, and because there's leftover, that box is moving. So when we draw this, you can see here that here's my box, and I've got here, this example is I'm pushing the box in one direction and Fred is pushing the box in the other direction. And if Fred and I are pushing the box at the same force, and you see how these arrows are the same size, if we're pushing with the same force, then the net force is going to be zero. And when we want to represent unbalanced forces, we have one arrow that's bigger than the other. And that way you can see there's a large force and there's a small force, and while yes, this is a subtraction problem, it is going to be able to be moving in this direction. So this chapter 11 is where we cover all of Newton's laws of motion. There are three of them, and the first one is all about inertia. So if you go through the official text, it's objects at rest remain at rest, and an object in motion remains in motion until it is acted upon by an unbalanced force. Now what that means is that if I am standing still, let's say a box is standing still, let's make it something that's not alive. There's a box standing still, and that box wants to stay still, and the only way that box is going to move is if it's acted on by an unbalanced force. If there's a force that pushes or pulls it in some direction, it's the only way it's going to move. If that object is in motion, say a ball is rolling and it's slightly downhill, that's going to keep rolling due to gravity until something acts on it that's either going to stop it or going to change its direction. So it has to get acted on. It wants to keep doing the same thing it's doing, and the only way that that's going to change is if it hits it, something moves it. If something's sitting still, it wants to stay sitting still. If something's moving, it wants to keep going that way. You can feel this in a car, and this is called inertia. And you feel this when your folks drive you around all the time. Inertia is the resistance to change in speed or direction of motion. So, for example, in a car, if you're going straight and your mom turns left, your body wants to keep going straight. And so while she's turning left, your body's going straight, so it feels like you start to lean to the right. But what that is you trying to go in the same direction. When your car stops, so you're going at, let's say, 30 miles an hour, and you come to a stop sign and they hit the brakes, your body wants to keep going, so it's going to lean forward. But the brakes are the force that's making the car stop. So you're trying to go forward, you lean forward. Then at the stop sign, when they're done, they hit the gas and your body wants to stay at rest. And the car is pushing you forward, so you lean back in your chair a little bit. And the larger the force, the faster you take off, the more you lean back in your chair. That's inertia. Driving. And that was section 1. We're going to continue with section 2 today just because they're both so short. And they will both be due on Thursday. So please, I'll let you know in class just so you have enough time to make this happen. This is force, mass, and acceleration. So we've talked about all 3 of these things now. We're going to start to connect them, and they connect really naturally with Newton's second law of motion. And this one states that acceleration increases with more force and decreases with more mass. This is your official definition, and yes, I do need you to remember which one's which. So what does this mean? Well, let's say that you're a guy standing on a skateboard and you're just standing on the skateboard and somebody else is going to push you. If somebody else pushes you harder, you're going to go faster. So acceleration increases with more force. You add more force, you push him harder, and he's going to go faster. Now, it also decreases with more mass. Let's say the guy on the skateboard, suddenly you put 7 dictionaries in his hands for him to carry. Now, if you give him the same amount of force to push him, he's going to go slower because it actually takes more force to push more mass. Does that make sense? So, acceleration increases with more force. The harder you push him, the faster he goes. And it decreases with more mass. If you make him heavier, you have to push him harder to make him go. Okay? And this is the whole skateboard thing. And more skateboards. All right. And look, more skateboards. Okay. So, this is what this looks like in a diagram type picture. So, the red is the force that you're giving the box to push the box across the floor. And if you have a small force that acts on it, it's going to go this far. And if you have a larger force with a bigger red arrow, it's going to go even farther. So you've got increased acceleration. And here, the box actually gets bigger and the red arrow stays the same. So you're giving these 2 boxes the same amount of force, and the smaller one is going to go farther than the larger one. And this is how easy it is to represent this in just a quick drawing when you're taking notes. There is an equation. Yes, there's more math. So our basic equation is force equals mass times acceleration. How hard do I have to push you? Well, that depends on how heavy you are and how fast you want to go. Now, again, we want to be able to flip these around. So the basic one is force equals mass times acceleration. And if you divide each side by acceleration, you end up with mass equals force divided by acceleration. And if you divide each side by mass, you end up with this third one. Acceleration equals force divided by mass. Now, the force is measured in newtons. And this is an actual unit of measurement, and it's represented by a capital N. And this is the force required to move 1 kilogram of mass 1 meter per second each second. So it's per second squared. A newton is the amount of push you need to give something so that it moves a whole meter. You know what a meter stick looks like, right? So it moves a whole meter each second. That's 1 newton. it has to accelerate one thing, like a box or something. It has to accelerate that thing by 1 meter per second each second. That's a Newton's worth of force. And that, of course, is named after Sir Isaac Newton, who discovered gravity, and that's where force all started. Now, forces can also change direction. You can do this with or without changing speed. You can give it a force that doesn't change its speed, but it does change its direction. And then we have a term called centripetal force. And this is the force required to move something in a continuous circle. Now, the force points both in a straight line and toward the center of the circle. This happens with like the moon in orbit around the sun, and the Earth and the Earth in orbit around the sun. So we've talked about this before at the end of 6th grade. It's the fact that the moon, let's use the moon for example, the moon wants to keep going in a straight line, but the gravity that's pulling the moon toward the Earth, that's a gravitational force. So you've got inertia versus gravity, and so it's constantly pulling it in a circle. That's centripetal force. And here's essentially what it looks like. You've got one direction for inertia and another direction for gravity, and it ends up sending it in one direction. And that's where we're going to stop for tonight. And we will pick this up. This is going to be due next week on Tuesday, sections 3 and 4. Okay? Thank you much. Have a good one. I'll see you next time.